Hello, Science 30s. I'm going to go through these notes on power and electricity transmission, and I'll try and do it as efficiently as I can. There's quite a number of formulas that you need to be comfortable with, but I want you to know that they are, I know I've written on mine, but they're all in your uh, Science 30 data booklets on page 3. And some of them I just embedded in the notes anyway, but I'll show you a few of those as we go. So power is the rate at which work is done, or it's the rate at which energy is converted from one form into another, and it's measured in watts. Okay, the most common reference for everybody is a light bulb. Light bulbs are rated in watts in terms of how much energy they use or consume per second. Um, there's issues with efficiency there, but don't worry about that for this. The three formula, or sorry, a watt then is a joule per second. You can see that right there. And be ready for some prefixes. None of them are too crazy. Again, if you don't remember them, look them up. But 1 kilowatt is equal to 1,000 watts. That's the very common or the very common prefix that we use. Now, power can be calculated in a number of ways. Uh, and they involve the aspects of electricity that we've been studying: current I, voltage V, resistance R, and energy, which is E, and then obviously time. Okay, because power is the rate at which we use or consume energy. So these are the formulas, and if you've seen them before, awesome. You can kind of fly through this stuff. But if you've never seen them before, just be really patient and don't feel like you have to memorize these formulas. It'll help you, but they're on your formula sheet. So as soon as you know you're dealing with power, if you see things in watts with a W, you're dealing with current and voltage, look to your formula sheet and find the relationship that defines the variables that are being presented to you. And then so you might have to manipulate one of the equations, but they all are like 3 variable equations for the most part. And so there's nothing, they're not crazy difficult and complex in that regard. So I'm really optimistic you guys can master these quite well with some practice. So the first formula, power is equal to current times voltage, and that can be manipulated to solve for current I or voltage V. Now, this kind of got cut off a little bit, but I want you to see that if you multiply voltage and current, okay, so if you multiply voltage and current together, voltage is measured in joules per coulomb, okay? That's how much energy each charge has. And current is measured in how many coulombs pass a point in a wire per second. So you multiply those two together, and as it shows there, those nice little hash marks, the coulombs cancel, and you're left with joules per second. And that's exactly what a watt is. A watt is 1 joule per second. So that's one of the relationships you'll use. Another one which builds off the same thing is we can say, well, yes, power is equal to watts, which is joules per second. So the other formula for power is just the amount of energy consumed per second. Okay. And sometimes we have time in hours, and so we have to switch from hours to seconds, or sorry, to go backwards or the other way. But just be aware that time is obviously relevant here. So an easy application that we will do shortly here is where we solve for energy. Energy is equal to power times time. And I included this little graphic. Often we measure energy in another unit that isn't joules, but it's kilowatt hours. Okay. And kilowatt hours aren't too hard to get because all you do is, instead of putting power in watts and instead of putting the time in seconds, okay, which is that's kind of the baseline. Those are the baseline units for joules and for energy, right? Because that's 1 joule. 1 joule is equal to a watt second, or watt times a second. If you change your power into kilowatts and you change your time into hours, okay, and power companies do this all the time. We'll do a question here in a second that uses that. You get another unit for energy, and that's kilowatt hours. And you'll see in the examples, they they write it as kWh like that. So capital W for watts, but lowercase k and lowercase h. Okay. Now, the last one is kind of a blending of the formula that we learned a while back for voltage. Okay, voltage is equal to, actually here, if you come in here, voltage is equal to current times resistance. And power, we just learned that before, is equal to current times voltage. So all we do is we actually substitute this amount right in there, which I showed in this intermediate step, okay? So we just substitute in I times R in for V, and then you get a new formula. Okay, so the I's will square, and we get a new formula to solve for power. Power is equal to the current squared, or current times resistance. That's what this graphic actually attempts to show you down here. And it just shows you that watts actually can be expressed in a couple of different units. A watt, like we said earlier, is a joule per second, but here's another one, okay? And it's just the units for the variables that we're using, right? So it shouldn't be that much of a stretch for you. If you have amps, current is measured in amps, and so you square that, you have amps squared, and resistance is measured in ohms. Okay, so there's the three formulas, and I will walk through examples of all three. We're going to go through examples of all three because you need to be comfortable with them. In every case, though, some of you that have taken physics from me before, I'm a huge fan of this GRASP method, and I'm going to model it a little bit as we go through these questions. The G stands for given. It's what is given to you in the problem. So if you read the question, there'll be some numbers in there and with units. Part of the skill you'll get really good at with practice is like, oh, you recognize what every one of those variables are. Okay, so that's what's given. R stands for what's required. So what is the question asking you to find? That is the variable that's not known, and so that's the one you're going to look for, and to do that, you're going to need to pick a formula, which is A. A stands for analyze, and what that really means is choose the right formula, okay? So this is where you look to your formula sheet, and you're like, okay, which formula will help me will help me resolve the question when I have these variables, okay? And S just stands for solve. Sometimes I like to say substitute, and that's where you substitute in the numbers for the variables, and then you get your answer. Now, P stands for paraphrase. This is often where you have to express your answer as a sentence, okay? So you have to actually, you get a number, you're like, oh, well, yeah, the voltage here is too much for this device because we've just calculated it, so whatever, okay? So often we just stop at S actually because you're just solving for a number, but you may have to define it, okay? So having said that, let's jump into some of these. So here's some power examples. A speaker can be treated as a device that offers 4 ohms of resistance. There's our first number. So that would be resistance to an AC input signal. And it allows only 2 amps of current to flow. So look at that. We have 2 variables. That's the given. And then it says calculate the power consumed by the speaker. So power is what is required. Okay. And so so step 1, actually this one, there's because we don't have the actually we could actually solve this problem using the other formula. I just realized that. So they opt to go this route. They're saying, well, we should be able to calculate the voltage first, okay? Because according to, you see this expression here, voltage is equal to current times current times resistance. So we have current and resistance. So I can actually, first of all, find the voltage, okay? And then so the voltage here looks like it's 8 volts. And then I can stick that into the power expression, which is right there. Voltage times current. So then I get 16 watts, okay? Now, actually, why I just paused there is because there's another formula that just we can calculate for power using the other one, which is I squared R, okay? And we could skip that step because The current is 2, so 2 squared would be 4 amps squared, and we multiply that by the resistance, which is 4, and that gives us 16 watts. Now let's actually see, is that the same answer as we got down here? Boom, look at that. Okay. Well, so there you go. It just shows you that we could, using the variables and the formulas, we actually solved that in 2 ways. Okay, because the relationships hold all the way across. So I don't know, we did that a little better than that example processed. So, well, look at that. Moving on. Here's another one. Actually, this one does do the same method we just did. So in this example, it says that there's 4 ohms of resistance in a speaker. So there's R again, and we actually are given the current again. And actually, this is AC current. So yeah, no, that's the same as the other one, just checking. So yeah, then the power here we could use, because I have current and I have resistance, then I can just use that guy again. P equals I squared over R, and so there we go. The power consumed by the speaker is 81 watts. Let's move to a couple other examples. So in terms of energy now, so those two were calculating power. Let's look at some energy examples. So this one says a kettle that's rated at 1,000 watts. Okay, so there's power. It operates for a total of 60 minutes in a typical week. So there's time. Okay, now it says calculate the energy. So just quickly scanning, and I know some of you have these sheets in front of you. There, we're looking at right there. Energy is equal to power times time. So coming in here, we will, if we want to get in kilowatt hours though, I need the power in kilowatts and I need the time in hours. So if you can see here in the solution, there she is. We did a conversion from watts to kilowatts. I love setting up those conversion fractions. I think they make a ton of sense because the units you don't want cancel out. So there's the power in kilowatts. Most of you can probably see it's got to times that by 1,000 anyway. Getting the time in hours, 60 minutes is the same as 1 hour. Probably most of you know that right off without even doing that. And we just got to multiply those two together. So lo and behold, we get 1 kilowatt hour. Okay. Now, the second question says determine the energy consumed in joules. So now what we need to do is when we're looking at E equals power times time, we need to get the power in watts and we need to get the time in seconds. Now, in this example, they actually converted watts, or they expressed watts as joule seconds. Okay. Now, the reason for that is they're actually looking to cancel out the seconds, which is what will happen. So some of you can maybe follow that anyway, but because if you multiply a watt times a second, you're going to get just joules. We talked about that earlier, right up here, right? Sorry. Yeah. So right here, a joule is equal to a watt second. I know that's a little ugly, but so anyway, they did the conversion of minutes to seconds, and those of you that took physics from me, 1 hour is equal to 3,600 seconds. You may have burned that one into your memory because it's a nice unit to remember. But if you don't remember it, you can derive it like this, no big deal. And so we're going to take 1,000 times 3.6 times 10 to the third, which gives us 3.6 mJ. Now, it's not Michael Jackson, but that's megajoules. Okay. So again, you see a big M like that, go find it on your sheet, and you can see that's times 10 to the third. Okay. Now, this little summary here, 1 kilowatt hour is actually the same as 3.6 megajoules. That is on your formula sheet. I'm maybe going to zoom in here so you can kind of see that. It's right there. Okay. The related value there. So you might be able to convert that in one way or another, which is actually that last question. What's the relationship between kilowatt hours and joules? We already said that. And then D, you could do an alternate method here. You could just say, well, I know what the ratio is. There's 3.6, times 10, 3.6 times 10 to the 6 joules in 1 kilowatt hour. So then I could multiply 1 by that amount, and then you get 3.6 times 10 to the 6th joules. That's a little redundant, but it makes the point that that's another conversion factor. Now, there's a point worth mentioning here when we're talking about electricity, and it happens in our homes with all the devices that we use, and the idea is something called standby power. It's worth mentioning. Standby power. Your electrical devices, a lot of them, they use a little bit of electricity all the time to have them in kind of a ready mode. Okay, so they're sort of in a sleep mode. And it's just so that it can boot up quicker, like when you need it. You don't have to wait a bit longer, or it's just power that's needed to show displays on, like digital displays when it's not even being used. So you can look at it at any time and see the clock or something. So here's some. What's interesting though is that all these standby powers add up, and if you're keeping track of your electricity bill, you can actually reduce it over a long period of time. You can reduce your electricity bill if you actually unplug your devices, and that's not always practical because sometimes you do want them in all the time. So this is a great list of things that can have this what's called standby power. Okay. If it has a standalone power supply, like an AC adapter, if it has remote control, soft touch keypad, if it's warm to the touch even when it's turned off, if it has a digital clock display, okay? So that's not really anything to answer, but these actually just capture examples of what is standby power. Now, the next question highlights the total standby power consumed by the devices in this girl's home, Michaela's. It's 87 watts, okay? That's the total power that is attributed to this standby power. Now, here's how the power companies work. The total energy in kilowatt hours required to supply all the appliances in this household with standby power for 1 year. How much energy is required? Okay, so let me just pull this out a little bit. So to determine that energy, we're going to look at energy equals power times time, and we are going to determine it in kilowatt hours. So the power is 87 watts. So I need to divide that by 1,000, or 87 times 1 divided by 1,000. So that would give me 0.087. Okay, kilowatts. And hours. Okay, this is 365 days in 1 year. So how many hours is that? That's a lot of hours. Okay, but what would that be? 365 days. There are 24 hours in 1 day. So I like setting up the fraction that way. If you're comfortable with that, the days cancel. Okay, and we get 8,760 hours. Okay, so we need to take that 0.087 kilowatt hours and times that by 8,760 hours. Okay, and lo and behold, that gives us 762.12 kilowatt hours. Okay, now I'm actually going to kind of clear some of that off so we have some room. All right, so there's our, you can go back to that if you need, just back up the video. So now that is the total energy for 1 year. Now the price. Oh man, in Alberta, we have awesome electricity. It's actually quite cheap. Compared to other parts of the world, we are very competitive, if not cheaper than a lot of places in terms of how expensive it is for the consumer, for people like us to pay for it. 9.3 cents per kilowatt hour, that's pretty cheap. But what is the annual cost in dollars for the energy required to supply the standby power for this house? So all it means is for cost, the company, the electrical company, they're charging you 9.3 cents per kilowatt hour. So I think most of you can see this pretty quick. If we have this many kilowatt hours, we just times that by 9.3 cents per kilowatt hour. Now it says determine the annual cost in dollars. So I would just convert the 9.3 cents into dollars right away. So that would be $0.093. Okay, just divide it by 100. There's 100 cents in a dollar. And lo and behold, then this should come to $70.88. Okay. So, $70, that's not zero. That's actually, you could, if you are attentive to that, you could actually save yourself a decent chunk of money by reducing your standby power if you can. Okay. But overall, here's the issue, and that's part C. The standby power is actually adding to the demand for electricity, which is also adding to the demand to produce it. And so, depending on the sources of our electricity, we could be polluting the air more because of our standby power. And you take, $70 doesn't sound like much, but you start multiplying that by every house in the province. Oh, it's a staggering amount of wasted energy. Okay. And so, there's room there for improvement, but we're all kind of power hungry. Okay. So speaking of electrical generation, that's where we're headed next here, just for a little bit. You need to understand generally how electricity is generated, because we're going to look at some of the calculations for voltage in the transmission lines, or like in the course of moving electricity from a generator to your house. So in general, you should just know that to generate electricity, we typically take a fossil fuel. In this case, it's showing natural gas. We burn that natural gas to create heat. That heat heats up water, which creates steam in a boiler, and that steam is pumped through these turbines right here and making them spin. And those are connected to a permanent magnet. This is simplifying it a little bit, but a permanent magnet right here. And if you move that magnet inside a coil of wire, then you cause current to flow in that wire. And that current is then transmitted over electrical power lines. And there's some other steps in between that we're going to learn shortly, so that can get to your house. In that process, we in Alberta, unfortunately, or fortunately, really, depends on how you look at it, 75%, about 75% of all the electricity generated in Alberta, at least according to the textbook source, comes from burning coal. And it's because we have so much of it. We'd be foolish to not harness it, because it's right beneath our feet, and there's a huge supply. Now it's a finite supply, and that's a problem because it's not renewable. But man, we have so much of it, and it's really easy to extract. The issue, though, is all coal has sulfur and nitrous oxides in it. Okay, and so if you look at this chart here, the type of emission, a typical generating station is listed here, and it lists the amounts in grams per kilowatt hour. So how many grams of this material is emitted per kilowatt hour of electrical energy generated. Okay. So we have some asterisks here. These here are actually the maximum limits allowed. So there's an Alberta emission standard. Obviously, the government imposed some maximum values to try and curb pollution, which is awesome. We definitely need that. But Alberta, there's a number of generating stations here in Alberta that are doing way better than that. And so this highlights an experimental low emission, generating station. You can see it went from 1,000 here down to 800. Okay, this is 1,000, 1 times 10 to the third, to 800. So that's a bit of reduction, 200 gram reduction. But hey, over a long period of time, that's a substantial amount of CO2 removed. Obviously, we want to get rid of sulfur. I've driven, on my way to BC, I've driven past generation stations, electrical generation stations, where there's just piles of sulfur. Like you can, now I don't know if it's by the station, but when they do extract it, they sell it and do stuff with it. But you want to rip out all the sulfur you can, so that stuff is not getting into the atmosphere, right? These guys here, these sulfur and nitrous oxides, those guys are bad news. That's what makes all the acid rain. Okay, so you want to reduce those as much as possible. So definitely better. But then look here, natural gas. Oh, natural gas is even better in terms of a fossil fuel. It's all the way down to 400 grams per kilowatt hour. The sulfur and nitrous oxides are crazy reduced. They're almost imperceptible. And then, yeah, sure, the particulate matter is dropped as well. So that's good. Now, natural gas is so much better for heating, though. As noted, like we're not using huge amounts of natural gas to generate electricity. It's much better to use for heating, and it's cleaner. So I'm not surprised that we're not getting the bulk of our electrical demand from burning coal. But you should just note that, Alberta's made steps to try and minimize our pollution, but it's not zero. Like there's still room for improvement. Now, in the process of generating this electricity here, we are going to, or there's an interesting lesson you need to learn here about transmission. And it's tied to this relationship. The power is equal to the current squared times the resistance. And in this case, the power lost in the cables due to heating. Okay, so heat, just like when you run current through your toaster, obviously that's a high resistance wire. So it like glows bright red and it cooks your bread for you, right? Turns it into toast. We don't want that much resistance in the power lines. These power lines have to be as low resistance as possible so that the current, or the electricity and current, yes, can be transmitted easily to where it needs to go. But we still lose power, or we lose energy due to resistance in the cable. Okay, so we can calculate that power lost using this formula, P equals I squared over R. We need to know the resistance in the cable in ohms, and you need to know the current passing through the cables. Okay, so we're talking about the high voltage power lines. Now, let's go through this first example here. So we got a 100-kilometer length of cable. In the cable, there are 5 ohms of resistance. That's actually pretty amazing. That's not very much at all. But the cable transmits 500 kilowatts of power from the generator to a small town. So the first question is, determine the electric current required to transmit 500 kilowatts of power if the voltage used within the system is 5,000 volts. Okay, so we have a voltage and we have a power, okay, in kilowatts. So we're trying to find the current. And they are related like this. Power is equal to current times voltage. And so, as you can see in the, actually, let's go down to this first solution. First of all, we get the power into watts. So we have to times that by 1,000. And then the voltage is fine. It's in volts. So to solve for current, we have to manipulate and divide the power by the voltage. So that's what we did. And we get 100. So it was 100 amps. Okay, that's a lot of current. Okay, any 100 amps going through your, anything in your house would light on fire. Like that's a huge amount of current. So anyway, part B then says, use your answer, we got that, to calculate the power loss due to the heating effects through the 100 kilometers of conducting cable. So in the power lost is going to be determined using this formula. We were instructed by that earlier. Okay, so the current is 100 amps, so we stick that right there. Power is going to equal 100 amps squared, though, okay, times 5. So that gives us 5 times 10 to the 4th, or I guess that's, 50,000 watts, okay? That's a lot. But the power lost due to the heating effects is 5 times 10 to the 4th watts, okay? Now, back in the question, though, it says, what percentage was lost due to the heating effects? So yes. So this question then says the transmitted power was 5 times 10 to the 5th. Okay. And where was that number? You know what? I think I cut that off, actually. Sorry that I don't think I got that from the, sorry. No, we did that. I'm sorry. I was trying to find that in the question. That's what we found in the first, the first part. It was 500 kilowatts or 500,000 watts. Okay. So that is that's the electric current required to transmit, that's the amount of power that's transmitted, 500 kilowatts. Okay. So that's 5 times 10 to the 5th. the power that's lost to heating, we just calculated that as 5 times 10 to the fourth. So we can do an efficiency calculation, which is what we're doing, the amount of power lost over the amount of power transmitted, okay, as a percent. So basically it comes out to 10%, okay? Now, you might think that's not too bad, 10%, I mean, but we're talking about money here as well. And I don't think that's very acceptable for electrical transmission. Electrical companies aren't too happy that 10% of the power is just like being lost to the air. They're losing money because they're not even collecting money on that amount of power loss because that's not on a meter. So that's not great. So here is the interesting solution. The solution, or a solution, is to change the voltage. Okay, so look at this. Example 20, problem 20, we're going to increase the voltage to 50,000. Instead of 5,000, it's now 50,000. Okay, so and we're going to do the same math. So now, how much current is there if the voltage is now 50,000 volts? Okay, so by increasing the voltage proportionally here, if you look at this, if you increase the voltage, then the current has to go down because the power didn't change. The power is still the same, but mathematically, if you increase the voltage, then the current has to drop. And so that's exactly what happens, because look, now when we calculate the current, it's actually 10 amps. That's crazy. It was 100 amps before, remember? So now it's only 10, and look at what happens here. So, whoops. So now, if you calculate the power lost using the P equals I squared R, this is kind of the killer, because when the current is squared, that dramatically changes. Anything you can do to reduce the current in this equation will reduce the amount of power lost. And look, we just did that. So the power is 5 times 10 to the second watts, okay, which is substantially less. So now you calculate the efficiency, and it's the transmitted power again was still the same, 500 kilowatts, or 5 times 10 to the fifth, but now the power lost is only 500 watts instead of 5,000, I believe it was. So now when you calculate the percent, it's 0.1%. Wow. Okay, 0.1% of the available power was lost. Now, this math was trying to show you something that all power linemen understand, and that is the higher the voltage, the lower the current. And because of this relationship, P equals I squared over R, especially for lost power, if you can reduce that current as low as you can get it, then you will lose less power due to heat. You'll lose less energy to heat. That's exactly why those massive, the massive power lines that you see, actually here, I'll show you this. Let's go back to this one. These massive power lines, these guys, when you see them on the road, on the highway, they're way the heck up there in the air. That's for safety, but they are huge. They're carrying like 500 kilo. The voltage is 500 kilovolts, okay? For most of those, that's even greater than this amount, okay? This amount here is 50,000. The highest ratings I've ever read were 500,000 or 500 kilovolt, okay? So that means they're just, anyway, the engineering behind this is really impressive, and we just take it for granted because electricity works all the time, but it's really quite impressive how all this works, okay? Now, so keep that in mind as we move forward. The last thing you need to learn here is actually on transformers. And you know what? I think I'm going to break this up, and I'll make a separate video just for this point forward.